moderate the. Um, let's kick it straight off. And we're gonna have an update from LVK first.
I will be doing that. Hello, Curtis. I'm Nicolas. I'm the Virgo Run coordinator. So I will share my screens. And now they should be in full screen mode. So that's going to be a brief update because I think we kind of knew at the last minute that there will be this meeting coming in. So we just gathered a few slides because we are quite busy those days. So maybe next time we could organize and anticipate better this meeting because it's quite important for us, of course. So just a recap of where we are in terms of O4. So we had O4A until January 2024 with CAGRA observing the first 4 weeks and then the 2 LIGO detectors. Then we had this long chunk called O4B from April last year to end of January this year with 3 detector network, the 2 LIGO detectors and Virgo. And basically on January 28th at 1700 UTC, we have transitioned from O4B to O4C. There was no break, just a moment when no detector was taking data. And this separation between O4B and O4C is related to the way we make public our data by chunks after some time. So currently we are in O4C, and the plan is to go on with O4C. I'll tell you more about that in a moment. And later during O4C, CAGRA should join the 3 operating detectors, and we should have part of O4C with 4 detectors taking data. So this is the map updated that you can see on this observing.docs.ligo.org/plan, which is updated at least monthly on the 15th of the month, and obviously more often if there are things to discuss. So this is the timeline for the 3 main collaborations, LIGO, Virgo, and CAGRA, and for the different runs. So we are somewhere here. So as I said, O4B just ended and O4C is going. And one thing important to report is that we plan to stop taking data currently from April 1st to June 4th. So basically all the detectors will go down for maintenance and commissioning work. The main reason for this break is that Livingstone needs to repair a big gate valve before the next hurricane season, because otherwise that could be a safety issue for the detector. And LIGO, Hanford, Virgo, and CAGRA will use this opportunity to make some work that can help improving things for the remainder of O4C and also anticipate in some way the O4 to O5 extension. In order to compensate for this 2 months break, it has been decided to extend O4C currently until October 7, 2025. Normally O4C should have ended on June 9. So it's an extension that basically compensates this 2 months break and also some unplanned data taking interruptions last year. And the plan is to have the gap unchanged between O4 and O5, with O5 currently expected to start in late 2027. Of course, that's still quite far ahead. So this date and more globally, the whole calendar will be refined and updated as time goes. So this is just a recap on the left of the number of public alerts that we have done for all of the different runs, not taking into account the breaks between those runs. So each color is a different data taking period. And the y-axis is the cumulative number of detections published until O3B. And for O4, these are candidates. And you can see that We exceeded 100 for O4B, and we are already at 9 for O4C. So overall, those 195 candidates for O4 are 216 total minus 21 retracted. So we have a retraction rate of 10%, which is lower than what we had in the previous run. And we have more than 3,000 low significance detection candidates. On the right-hand side of the slide, you have one example for our recent alert, S250206DM, which is binary neutron star major candidate. And that was obviously scrutinized very well within the LVK and also by our colleague astronomers. We had some technical issue with the data of the Virgo detector, but we finally managed to include them. And we think that having this alert treated as a tree detector is better for sky localization, etc. So we had several GCN updates, and I think the most recent one are summarized here. And at the bottom of the slide, you have links to the different circulars by the LVK and by all the other circulars that are associated with this gravitational wave trigger.
Nicola,
So
we have a question if you want to take that now.
yes, please.
Go ahead, David.
Yes, with regards to the delay between O4 and O5 not changing, do you mean that the start date for O5 will remain as it previously was, or do you mean that the duration of the gap will stay the same so that because of the later end of O4, O5 will start a little later?
Sorry for not having been clear. I mean that everything translates in the same way. So as written here, the gap remains unchanged. So if we we extend O4C by 4 months, so everything shifts by 4 months.
Okay, so O5 will start 4 months later than previously scheduled.
Yes, that's my understanding. So
Thank
currently
you.
late 2027, whatever that means.
Thank you very much.
You're welcome. Okay, so as I said, one new thing important for the OpenMMA forum, I think, is the fact that we are introducing subsolar mass or SSM alerts. So we've been working on that for a while, and the plan of the three collaborations is to activate those alerts in low latency relatively soon, in late February or shortly thereafter. So that will inform the identification of the JW compact binary merger candidate, in which the mass of at least one compact objects in less than one solar mass. So there will be a new source property as SSM, which will, as you can expect, provide the probability of presence of at least one subsolar mass compact object in the binary merger. So I think that the updated version of the LVK Public Alerts User Guide has just been published by Leo Singer a few minutes ago. So if you follow this link, you can already check in what the details of those SSM searches are. And I think there is also a supporting email by Leo, which is summarizing the differences in the user guide between the previous version and the new one. And as always, there is this email address that you can use if anything in the guide is not clear.
We have another question.
Okay.
Dave, go ahead.
Yeah, this sounds very interesting. If you go back and look at O4 and O4A and O4B, would you have seen any SSM alerts? Should we expect SSM alerts on a regular basis?
That's a good question. I'm not prepared for that, so I don't know what I should answer. No, that doesn't preclude what the answer is, but I don't know if I can speak about that. I don't know if we have spokespersons online or someone who can take that on my behalf. Jenny, yes, please.
Hey, this is Jenny. I've spoken to this group before, Operations Division Chair for the LIGO side. Any such answers, I think, to that question would come out in our catalog when we release the catalog. And the public release date for that, Nicola actually has in his secret spare slides, slide 10. So the 04A data release date is August 2025. And so we'll be more prepared to answer that question when the catalog comes out, is my current understanding. I hope that helps.
Thank you, Jenny. That's what I think I would have said, but it's better if you say it. Okay, so this is just a basic example showing you what the JSON payload for an SSM alert would look like. So basically, the search type will be different, subsolar mass, and you will have this as SSM property. And you can note that in this case, as remnant is not computed. And for those searches, the PSTRO classification will not be present. So that's the kind of payload you can expect for those new alerts. And the last thing we have for today is that for the next OpenMMA meeting, we would like to request one slot for Keita Kawabe, who could present the results of the poll LVK's rapid response for well-localized BBH candidates that he has circulated around the new year, and for which more than 10, I think, collaborations have replied. So we don't have this report ready today, but we already would like to thank the astronomers for their valuable input. And we ask for a slot next time so that Keita can go through the results of this poll. And that's all I have for today.
All right, thank you so much. Other questions? Go ahead.
I assume it was to me. This is Zsuzsa Marka from Columbia University, and I am asking a question regarding 0405, actually. I would like to know how LVK is preparing for open data during 05. There is a significant and actually real expertise outside of LVK. Now we are 10 years after the first detection. And lots of people can do this analysis, what the current low latency team is doing. So I think HFT and actually rest of the several 100,000 data channels are ready to be released publicly in real time. I would like to know how LVK is preparing for that, since the data and the detectors are paid by the taxpayers, and we do have a right for that data. Thank you.
I think the plan at the moment is to release data by chunk of 1 year with I don't remember exactly how many months of latency, but that's basically what we are doing at the moment, and I think that's the current position of the LVK.
I understand that, and I sort of knew that, but I am really encouraging the LVK to reconsider this position, because there is expertise outside, and this can be done, and the community is looking forward to fully open and public real-time LVK data. Thank you very much.
Point taken. Thank you.
All right, Dave, I do see your question, but I'm also I'm gonna do them out of order. E. Katsavondis, would you like to ask your question out loud?
I'm sorry. This is Eric Katsavonidis, MIT and LIGO Laboratory. I just wanted to clarify maybe what David was asking earlier. was how we're going to operate the SSM certs, the subsolar mass certs. And while we cannot know, or we cannot make any statement on the events that we're going to be collecting, I think, and I guess I'm asking my LAGO and Virgo colleagues here, that we're going to be operating the certs at the nominal false alarm rate as the rest of the certs. Maybe this is what David and the broader community wants to know from LAGO. And maybe my LAGO and Virgo colleagues can comment on that, or confirm that rather.
All right, does anyone want to respond? Like, yeah, Deep.
Yeah, the false alarm rate for the SSM alerts, whenever we enable them, at least right now, the value is 1 per year, so slightly more constrained compared to the nominal all-sky searches, the all-sky alerts. So yeah, slightly different compared to the all-sky, but yeah, I think I'll leave it at that. And this information is there on the user guide.
And then Dave Cook, do you want to ask your question to kind of as follow-up for that?
Yeah, mine was more of a technical question. And I was just wondering if any mock alerts are going to be sent out in the stream so that we can test pipelines, make sure that, nothing breaks.
Maybe I'll follow up. So the answer is no, in the sense of the hourly alerts that you may be receiving. Unfortunately, we haven't had the time to bring that up for the SSM alerts. However, the alert content for all 3 formats is available on the user guide. So if you want like an example packets, pretty much the screenshot that was shown, that's available on the user guide in terms of Avro, JSON, and XML packets.
Okay, that's fair enough. Thanks.
All right, do 2 more questions and then we need to move on. So Dave Coulter, do you want to say some to ask your question out loud?
Sure. I mean, it wasn't really a question, more of a comment that, like, while I appreciate, having access to a new class of object like these subsolar mass objects, it still would be quite useful to just even a rough estimate of the total system mass, especially for this latest event, DM. I think that there, definitely was a case to be made for optimizing your search depending on what that total system mass was. So yeah, I know I'm probably just preaching to the choir here, but it would be really great from the EM perspective to be able to say, or to know about the system mass.
Go ahead, Gene.
Just to say that thanks for that input and heard.
Great. All right, and then Shreya, why don't you ask your question? And we're gonna have to move on shortly, though.
Okay, sorry about the noise. So could some event candidates that have had SSM greater than 0 also have some classification probabilities? Because the event was picked up by other pipelines and could also be having some probability of being a neutron star.
Maybe I can take that up. So no low significant alerts for SSM. It's a very new search, so we are not enabling the low significant ones.
Okay, thank you.
And all right, I was on the fence on this one, but Wenfei, I think it's important enough that why don't you go ahead and ask that and see. We can have a brief answer now, but we can extend discussion in the chat or offline.
Okay, sorry, everyone's favorite question. Was just wondering if anyone could comment on, have there been conversations about wiggle room and timeline or given the anticipated uncertainties in US federal funding?
Yeah, go ahead.
This is the kind of thing that probably a spokesperson should answer, but we don't have anyone on the phone. So I'll take it. Everyone's favorite answer, shrug, I don't know. Because as you say, it's quite uncertain. At this time, there are no updates beyond what Nicolas shared a few minutes ago. So at this time, with what we know right now today, yeah, not no planned changes to O5 based on funding or anything like that. But as we learn more, as always, right? Like, even we learned that this gate valve is an equipment safety risk at Livingston. We learned more. We had to change. If we learn more about funding, we may have to change things. But at this time, the current plan is to stick with our current plan.
Okay, great. Thank you.
Yes, thank you very much for all the discussion. Thank you, Nicolas, for the presentation. All right, so let's move on and talk a little bit about O4 neutron star black hole binary neutron star prospects from Ved.
Hi. Okay, I'm gonna share my screen. Okay, can everyone see the slides?
Yes, we can see them.
Yes, we're good.
Okay. Yeah, so today, my name is Ved Shah. I'm a first year PhD student at Northwestern, but today I'm mostly going to be talking about work that I did as an undergrad at University of Illinois, Urbana-Champaign. And I'll be talking about this flexible framework that we built for predicting kilonova detection rates for current and future observing runs, and also talking about how this gives us insights into comparisons between the O4 and O5 observing runs. So I'm gonna go over the slide very quickly because I think everyone here already knows about it, but 170817 is where the kilonova story for gravitational wave localized sources really starts. It was the first time we found gravitational waves, a gamma ray burst, and an optical counterpart from a binary neutron star about 43 megaparsec away. And I think the important part here is that not only was this the first kilonova that we found using gravitational wave localization, but the only one. And this means that it's been over 7 years since we found such an event. So that begs the question, how many kilonovae can we expect to see over the course of O4, O5, and future observing runs? And how do the strategies between O4 and O5 compare based on current sensitivities for O4 and the predicted sensitivities for O5? So to answer this question, we came up with a pipeline. So starting from the left, we begin by sampling various parameters of our coalescing binary system. That includes things like the masses of the neutron stars, the inclination of the plane of the merger, etc. And we use this information along with the sensitivities and uptimes of the instruments to determine if the gravitational wave produced by the merger would be detected by the LVK network. If the gravitational wave can be detected, then we compute other parameters of the merging system, like the properties of the ejector. These parameters can be used in conjunction with existing SED grid models, like the ones developed by Buhler in 2019 to generate synthetic SEDs for each merger. And we also treat these SEDs for both Milky Way and a host galaxy extinction and redshifted to account for cosmological effects. Next, we convolve the SED with the transmission of our chosen passband to produce light curves. And then we use the limiting magnitude of some of the most sensitive surveys to determine if the kilonova would be detectable or not. Since there's a lot of parameters and underlying distributions involved, we use Monte Carlo trials, and we basically run many instances of this whole simulation until we converge on a solution. So I did mention briefly that we use many different distributions for sampling all of our parameters. There's about half a dozen different distributions for this simulation, everything from the masses of the primary and secondary neutron stars, the host galaxy extinction, the BNS merger rate itself, because that has large uncertainties associated with it, the uptimes of the LVK instruments, etc. And frankly, there's a lot of details associated with each distribution. I think certainly way more detail than we have time to go over today. And the distributions themselves are not particularly informative or interesting for the discussion that is relevant for this group. So I'm going to skip the details for now and redirect you to the papers, or you can maybe ask me questions about it after the talk if you're interested in knowing more. But essentially using this pipeline, we can answer questions about how many discoverable kilonovae we expect during O4. And for the middle 90% interval, we're talking about 0 to 5 events with a median of 1. I think this is not entirely surprising in 2025, given how O4 has progressed, and that it's been running for a while now. But back in 2023, when we first wrote this paper, this was certainly on the low end of the estimates for O4. And because we run these simulations and log all of our data, we have some distributions from the simulations. Going from left to right, we can see the distribution for the number of kilonovae, the distances, and then the peak and discovery magnitudes for all of our events. And these are colored. So for each plot, you can see multiple distributions. These are colored by the number of detectors, the number of gravitational wave detectors in the LVK network that were able to observe the merger. And if you look at GW170817, it's certainly on the tail end of our distribution. So it's a pretty unusual event at 43 megaparsec. So will things get better in the future? Potentially. So if we can hit the targeted sensitivities for O5, then we expect to see nearly an order of magnitude improvement for the number of discoverable kilonovae. And when I say discoverable kilonovae, these are events that will have a peak magnitude higher than the limits or the thresholds of our most sensitive optical instruments. So there are a lot of caveats with this order of magnitude improvement, and I will explain this later because I really think that we need to discuss how this improvement translates to being able to find real kilonovae. Okay, so once again for O5, we have the distributions of the number of events, the distances, and the peak and discovery magnitudes. And we have the addition of CAGRA, which we, because of its small horizon distances for BNS, we can basically ignore that detector for O4. Once again, most of the events here are found a lot further than 170817 like events, and 1 and 2 detector events carry most of the probability for finding events in O5 too. So the 2 LIGO instruments still have the best range, and that means that most of our advantage of O5 compared to O4 comes from the increased sensitivity of the 2 LIGO instruments. It's also worth noting that on average, a kilonova we find with O5 is a lot fainter and visible for fewer days compared to O4. because they're typically further. So this is just a direct function of being able to find events in a larger volume, but that also means that they're more distant and thus fainter. So when we are talking about that order of magnitude improvement during O5, we really need to consider all of these other factors that go into finding these events and things that would potentially make it harder to find kilonovae during O5. So since we had the framework built already, we thought it would be interesting to see what the framework has to say about past observing runs. So we ran the simulations for the O2 and O3 configuration, and we found that our numbers are generally in agreement with what we observed within our uncertainties, obviously. So about one binary neutron star merger with 0 kilonovae in both observing runs. And this is in line with the fact that 170817 was such an outlier in terms of distance. Okay, so let's attempt to answer another question about optimal strategy going forward. Really, what we want to do is see if extending O4 makes sense. Like I said before, this framework we created is pretty configurable, so we can change the type of question we want to answer. To understand the difference between the O4 and O5 observing runs, we can set up a new simulation to answer different questions with relatively minimal work and changes in code. So once again, starting from the left, we begin by sampling various parameters for coalescing binaries. And we use this information to calculate secondary parameters like the ejecta mass and the lanthanide richness of the ejecta, which are used to approximate the SED. Just like the first set of simulations, we produce light curves, and then we determine if the EM counterpart is detectable. Where the strategy diverges from the first set of simulation is that we run the test to make sure that the gravitational wave produced is detectable by O4 and O5 after we make sure that the EM counterpart is detectable. So there's a slight change in order. And once we compare once we run the test to determine if the gravitational wave the merger produces is detectable by O4 and O5, then we can compare the results between the two observing runs. So we can do an apples to apples comparison between O4 and O5 by keeping all other variables constant and only changing the LVK sensitivities and runtimes. And once again, since we have a lot of underlying distributions, we run a lot of trials until we converge on a solution. So using this method, we can get cumulative density plots to find the days to first kilonova detection for both O4 and O5. And on the x-axis, we have the number of days from the start of the observing run to the first kilonova. And on the y-axis, we have the fraction of trials that have a kilonova on or before this day. And we can see that typically O5 has a kilonova detection in fewer days compared to O4. Since we're interested in doing this apples to apples comparison, we can also find the difference in the number of days to first kilonova between O4 and O5 when all other variables are kept constant. So we keep all other variables you see in the top table here to the right, constant between O4 and O5. And we consider the same set of merging systems at the same distances, producing the same light curves when we're comparing the two observing runs. So the only thing that we change is the sensitivity of the LVK instruments, so the PSTs, and their uptimes. And then once we consider the same set of systems, we can find the difference in time between O4 and O5, which you can see on this plot to the left. So because of different uptimes, there are some cases when O4 is up and O5 isn't due to just dumb luck. And we would catch a kilonova in O4 before we catch it in O5. But you can see that this only happens about 20% of the times. Most times, O5 has a detection about 4 months before O4. So O5 certainly will give us a kilonova sooner. The problem here is that LVK05 updates are proposed to take about 2 years to finish, as we heard earlier today, which is marked by this red line on the plot. And if we factor in the 2-year time required for upgrades, then in about 88% of our trials, we would actually be better off just running O4 for longer. And so, yes, O5 gives us advantages in terms of finding events sooner. But if you factor in the time required for upgrades, then this advantage actually flips over to O4 configurations. As I said before, because O5 will help us let us search larger volumes, the average kilonova in O5 will be further than ones in O4, and thus they will be harder to find. So we will definitely have fainter events, but we might also have events that have poorer localizations and have fewer days at which for which they are discoverable. Okay, so in summary, so assuming the 2-year downtime between observing runs, in 88% of our trials, we are better off letting LVK04 run for longer if kilonova discovery is our top priority. Recent events such as 250206 DM show that O4 still presents some promising opportunities for the search of EM counterparts. And the advantages in kilonova discovery from O5 upgrades are likely exaggerated due to the increased difficulty in finding these events at larger distances. That's all from me today. The papers that this talk was based on are both out. So please go read them, and I'll be happy to answer questions.
Yeah, this is great. We have a time for a couple questions, but probably only a couple minutes. Go ahead, Alan.
Hi, Ved. Thank you for the nice presentation and for the excellent work. I wanted to comment that it's true that events will be more distant in O5. On the other hand, if Vera Rubin makes it, we will have much better suited instruments for the follow-up in the optical, which seems to represent a very big advantage, doesn't it?
Yeah, so if we have instruments like LSST, then that would certainly provide an advantage. And we actually did factor in the fact that O5 will have instruments like LSST up, which will give us an improvement in sensitivity. The problem is there's still cases when you cannot access localizations for an event using those newer instruments, right? So yeah, so even after we factor those changes in, the improvement does not. I guess we need to consider all of these other variables, because when I presented the numbers and we saw that order of magnitude improvement, we are not considering other observational inefficiencies in that process. So yes, there will be some improvement because of new instruments, but we already factor those in.
Thank you.
Shreya.
Hi, Ved. Great presentation. Could you actually elaborate a little bit more on that? Basically, um, how do you factor in the sensitivity of various telescopes? I know it's a really complex problem because you have the localization sizes and you also have the distances to the gravitational wave events and then the sensitivities of various instruments and observability. So can you talk a little bit about how you actually did this?
Yeah, so for the gravitational wave, and we took the most updated PSDs for O4 and the targeted PSDs for O5. And we used those PSDs with the Taylor F2 waveform from each system to see if they would produce a detection on the LVK network with a signal to noise ratio of more than 8. So that was the gravitational wave detection. And then for the EM counterpart, this is a lot trickier to model properly, right? Because as I said before, there's all of these human elements and human observational inefficiencies. So we do take into account that sometimes your 50 and 90% localization might be behind the sun. But beyond that, when it comes to events like 1904-25, where we had a good localization and we still couldn't find the event, it's really difficult to understand how to model that. So that's why we call these events discoverable. They sort of represent us working at 100% efficiency and not having any loss in events due to observing constraints and inefficiencies. Because ultimately, we just don't have enough priors to model that process properly.
Yeah, this is really great. So thanks so much, Ved. Unfortunately, we have to move on, but this is really interesting work. So next we have Chris Weaver, who's going to be doing some demonstrations.
Hi, hope my audio is working correctly.
Yeah, we can hear you.
Okay, great. So yeah, my name is Chris Weaver. I'm at Michigan State University, and the thing that I'd like to demo a bit today is some of the various services that we are creating and supporting through the SCiMMA project. So bear with me for just a moment here. I will share my screen. I'm going to be jumping around a little bit. Okay, that looks like it's probably showing up. All right, so for those unfamiliar, this is our main project page for SCiMMA. You can read it anytime you like. I'm not going to insist on dragging you through all of that. I'd rather dive into the internals that we have of the various services that you can use. So the central point for a lot of that is logging in right here on the page. I'm going to do that in a second tab so I can go back. So this gives another listing of some, although not all, of the services that we operate. Just to get it out of the way quickly, I think everyone here on the OpenMMA call is familiar that we do some organizing for the OpenMMA community and is probably on the mailing list, but one way to manipulate your mailing list subscription is through this interface. But moving on to some more science-oriented things, the first thing I'd like to show is the Hermes service, which you can access here. I would note also with this login, to save time, cheated a little bit. I was already logged into these pages. This just uses CI logon, so you can log in with your institutional identity, ORCID, all that sort of thing. So moving on to Hermes, this is intended to be a really easy to use web interface, as you can see, for viewing and interacting with and sending multi-messenger alerts. And so all of the data that it works with is public. I am logged in already here to this front page of it, but you don't need to be. Everything that I'm going to show here is something that anyone can see, even without an account. And so you can see that this system is ingesting alerts from a great many different data streams. There's a whole list of them here, and you can see many of these are mirrored from GCN. We have some other various ones that are going through other parts of our SCiMMA infrastructure, and that it's easy to view and look at these through this interface. I'm going to see if I can pick out here a data stream with which I personally have some familiarity. Let's see, let's look at the IceCube bronze quality track events, because I know there was one of those that happened recently. So having picked out a data stream that is of interest to me, you'll notice it narrows down the number of alerts that are shown, and I can pick out one individually, and I can see all of the contents that were included here in it as it was sent out via GCN and AMON. So that gets you basically all the data that you might be familiar with for these channels. I guess I'd also like to show that these can take some significantly different forms. One of the other aspects is that, as I said, messages can be published from Hermes itself. So there are some streams here that include that. This one, to be honest, I don't know what this data is particularly, since I'm not really conversant with it, but as an example of data that has been published with Hermes and is structured and therefore interesting. So we can see here there's a description of what targets were included in this, and here's the actual photometry data that was included in this alert. So just to give an idea of the breadth of data that's available here, besides just sort of the textual GCN form. Of course, it's also possible to obtain these things in a machine readable form. As you can see, there's this JSON option, and Hermes has a full REST API that's all documented through the About page if you want to interact with it that way. The other thing, besides viewing data, since I am logged in as a registered user, and there are no further requirements, you just have to be a registered user, I can also come over here and I can, in theory, submit a message. I'm not going to actually click the submit button at the end of this because I don't have any real data put in, but I can try putting some things in. You will notice that it does a good deal of validation. So the first thing was I didn't have a title for my submission. So that was red and the submit button was disabled. Now that I've entered a title, it's valid. And we have all of these different forms of information that I might want to include. So for instance, I can note a target. And again, there's validation to ensure that I put something that is not at least of the wrong form in, although I don't have any meaningful data to put here. But I can enter things, and it's enforced that's not structurally wrong. Likewise, there's a more advanced interface if you have this in a more detailed form. And there are all these other forms of data that we can enter. So as you saw, I could by hand enter a bunch of photometry data, for example, and there are also options to upload data so that you don't have to type everything out by hand. The other interesting aspect is I have a choice of where I send this. There are several different topics within Hermes that every person is authorized to send to. And Hermes integrates with both TNS and GCN. So by flipping these switches, I could, in principle, submit a message to those services as well. It's noted here that for TNS, Hermes is allowed to do that as a generic user. For GCN, I would have to have an actual GCN account that is authorized to send, and I would have to have set up the linking in my account, which I personally do not have and have not done. So that's just a really quick tour of being able to do things in this graphical way on the web with Hermes. One of the things that is powering Hermes internally is the Hopscotch service that we provide through SCiMMA, which is an Apache Kafka pub subsystem intended for multi-messenger alert information, but in fact capable of carrying any information. And we manage some of the lower levels of that through the internal portion of our main page here. So if you're a user, you can use this other button and see all of the things that you might want to modify with your user account and credentials for that pub subsystem. This is my main account that I use for doing work on this more or less every day. So I have a lot of stuff already populated in here. You can see that, for example, I already have a bunch of credentials. There are also a listing here of all of the topics that exist in this system to which I have some kind of access. You can see that some of these are public. Most of these, in fact, are public. I happen to have some unusual system permissions because I'm one of the developers. But I could browse through all of these different things that I can access. Some of them are actually private. And you can, in fact, see the internal Hermes topics here, too. And there are groups that are used for organizing. Basically, we support both public data channels, like the ones that are shown on Hermes, and private data channels. And so groups are the entities that own private data channels and can be granted or can grant access to other groups to work with those channels, both sending and receiving. Finally, where the rubber meets the road, I need to have an actual credential to be able to contact the service programmatically. I have several of those that I use for different purposes, and you can, through this interface, for example, manage those. You can see here for one of mine that I have allocated it certain permissions to be able to do non-default things. In our system, any credential can be used to read any public data, but to read private data or to write anything requires specifically assigning that capability to a credential. So again, there are a lot more things that you can manage and manipulate here, but I wanted to give then a quick example of if you drop down to a lower level than the Hermes web interface and want to do some things from the command line or programmatically, that we have a bunch of tools for that. So I have hopefully a clean environment here. So I want to demonstrate nothing up my sleeve. I'm just going to install everything that I'm going to use right away. So I'll create a fresh Python virtual environment with nothing in particular in it. And our main software package for this is what we call our hop client. So I'm just going to pip install that, and it will produce the probably familiar looking output there for a few seconds, and everything's installed. So very easy to do, just touch of a button. Of course, I use this stuff every day, so I have already worked with this a fair bit. I already have my hop credentials installed on this laptop, so I can use the various commands provided by the hop package to interact with those, just to show I've got various credentials here for interacting with a few different Kafka services. For example, our main SCiMMA hopscotch service lives at this URL, kafka.scimma.org. We also have development infrastructure that we use for testing things so that we won't mess up anything that's being done with the actual astronomy work, and so on and so forth. So this means I have the capability to connect to various Kafka systems. So let's show an example beginning to do that. Much like in the web interface, I could see what topics were accessible to me. I can also use this command line interface to get a list of all of them. And you can see here again, there are lots of these topics that are public, and also a few more esoteric things here that are private at the bottom, mostly test things because I'm more doing code development than doing astronomy here. But you can imagine that this would enable doing private astronomical analyses as well. So with these command line tools, there are basic ways that you can directly access the actual data. So I'm going to, for example, subscribe here to what's in our buffer of the GCN alerts from Fermi on one of its several streams. And after a few moments, we start to get some data. So you can see that there's actually stuff here. We keep about a 1 month buffer in Kafka. We have a longer term archive, but this means that if you want to grab something from a few days or a couple of weeks ago, it's just right there in Kafka with the same low latency interface. And so obviously you can do a lot of things with subscribing to the data besides printing it to the screen. That wasn't terribly useful, so I'll just stop it. Also, I can use this interface as a simple way to publish alerts and messages. So suppose I have some sort of alert here that I think it's very important that people in the community know, and I want to send it. So I'm going to, in fact, start in my second terminal window here, an instance of the client listening for this. I'm going to route all this through our development infrastructure just because I'm sending, obviously nonsense data. So I don't want to pollute the main system with that. But there's no actual difference here from how this would work on the production system to which everyone has access. So we have one terminal there listening, and on the other, we're just going to say we're going to publish to this particular topic on that dev system, some topic name, this file that I had. It takes a moment to make the connection, but actually sending the data is quite rapid, and this is with just the basic tunings of these command line tools. I can also send much larger things. So for example, I have a multi-megabyte file that I want to send here, and this is a new feature we're very excited about that was just enabled in our new software release yesterday, that I'm going to send something that's actually too large for the Kafka topic I'm putting it through. And so this is a feature of our client that it will automatically detect that. We have a companion service that allows offloading those chunks of data that are just too big, and it sends a simple message in its place over the low latency channel of Kafka to say that the actual data is present at this other URL. So I can send this. Oh, I was going to do something to show when the file arrived. Well, I can still do that. It may be too late, but
yeah, I think we should wrap up if we can.
Just about done. So, okay, file has arrived, and you can see, so I just sent a 28 megabyte file through a Kafka topic that I'll just tell you happens to have a size limit of 1 megabyte approximately. All right, so that was pretty much it. Just a whirlwind tour that we have this command line interface. Much more power and control if you use this as a Python library, and then you can build your own tools sending and receiving data. The last thing that I want to show really quickly, I'm sorry for going a little over time, is that I would like to show one other service that we have, which is Blast. It doesn't integrate as much with Hopscotch, so it is linked in a slightly different place. So this is an automated service characterizing the host galaxies of observed transient events. The analysis code is, as I understand it, primarily by the transients team at UC Santa Cruz, and the web service is operated by NCSA in Illinois. This is the page for it. And this also is generally public. I'm not logged in or anything here. And you can see all these different transients that are being processed. And this service has been running smoothly for, I think, something like a year now, has processed several thousand transients. We have ones that have just been processed, ones that are waiting and will hopefully be ready shortly. And so for any of these, we can pick an event, click on it, and we can see just a wealth of different data about it here. We can see some of the sky maps, various different forms of the information, both from the input and the output, I believe, of the analysis. Of course, all of this is available in machine readable form. There's a download button over here. And there is also a programmatic, I believe, REST API to this system as well. So I think I've gone a little over time. I'd better stop there, but I'd be happy to take any questions that people have about this set of services.
Yeah, I think we're out of time for the meeting now. So, but if you do have questions, please send us email, send us messages on Slack. Otherwise, thank you very much for coming to this OpenMMA meeting. We will talk again soon. Keep an eye out for the next meeting. Thanks.